Okay, welcome back, everyone. I see there is a subset of everyone is missing. So, or not, I don't know, the room is too big. Anyway, so as per the agenda that we shared with you, Dr. Mohan Thota was supposed to give this lab session, but then because of some official matter, he will be doing it. So I was supposed to give it tomorrow. So we have just did a mutual agreement that I'll give it today, and he will give it. He will give his lab tomorrow. So it's this one is none of you is from Bangalore or okay. Oh, you are okay. We have few. So do you know in person this about this event? No? Did I made it up? Okay. Okay, maybe it was not that big then. But then it's, along with me, IMD also will have to be wrong. So, so anyways, so I'm gonna just give you a brief idea of like how we can see an event around us, like for a heavy precipitation event. Yeah, I didn't write precipitation. I just wrote extreme event. By seeing the month, you might as well think it's an extreme heat event, but it's a extreme rainfall event. So yeah, I will just describe a little bit before going into the analysis. And I have a Jupyter notebook that all of us have laptops. Okay. So yeah, you can wait. You don't need to open it as yet. And then we will just go through my notebook block by block. And then along the way, we will just do some hand raising. Who wants my code and who wants to write themselves? So yeah, this was the precipitation time series that I did not plot. I just used, just quickly, I don't know how many of you know, this is a NASA data visualization web portal that you can, you need to log in, otherwise there is a memory limit. But once you log in, there is still a memory limit, but it's much more relaxed than if you didn't log in. So, and then you can use this portal to do some quick visualization of different data sets. Like, for example, some satellite data set, maybe some of the data set that Courtney presented to the morning, you can actually very readily visualize those. Maybe not for a long time, because of course we will have a memory limit. But I find this very, very helpful if I have to just quickly look at things like precipitation time series, like I did this one. Some of the details are written here, but never mind. It is just GPCP rainfall time series for like from 10th May to 21st May. And I had taken a region which is 75.989 east to 77.967 to east and 12 to 14 north, roughly, which those who know their map well would know this falls over Bangalore. And yeah, this is the rainfall time series, and you can see there is a peak on 18th May and yeah, even though I said it 19th May extreme, because how you count these extremes, like when it happens, in some data set you would see if it is like whether it's the current day data is recorded as current day, or it was the previous day's last 24 hours accumulation that is reported on today. then based on that, it might differ a little bit. But nonetheless, we can all agree that there was some heavy precipitation, and this is millimeter per day, 35 millimeter per day. But if you look at IMD records, actually, you would find larger amounts of rainfall happening on that day. And yeah, so this is just a couple of images to show that I was not wrong. There was some, but like any other Indian cities, it can have waterlogging for a very little amount of rainfall. But still, this is, I took it from, if I'm right, it was not a media report, I guess. I forgot to put the source. Oh yeah, it's mint, it's mint. But so IMD maintains a Facebook page. I don't know if you know about it. So IMD has this weather report, weekly weather report, and they provide some information about the weather. And if you click on those links, I mean, you cannot click on them now, but if you can, then you would see IMD reports on 19th May and 21st May. And then you will see that during that time, there was extreme events happening over northern Karnataka and some southern Maharashtra kind of thing. And there were, yeah, so. One more point I wanted to point out is, so on in the year 2025, I mean last year, monsoon onset over Kerala happened. I should have made it in a bigger font. So 24th May. So this was 5 days before monsoon onset, much northern, north and east compared to Kerala. So this is not really part of monsoon system yet. I mean, assuming we agree that monsoon onset over Kerala, I mean, it doesn't really define instability over the whole region, but still. And again, the point is not to like see the overall large scale or different mechanisms, at least at this point of this event. I just wanted to use this 1 hour to discuss like how we can just plot a different diurnal or different features of an extreme event. So like a case study, and I think this is not the end, this is just end of the presentation, because I'm gonna go to my notebook now. So this is what we're going to do. I mean, this is our outline of my notebook. So we're gonna load the data from Google Drive. So I have kept the data on my Google Drive. So that might be an issue for you, but I think I have figured out a way to do it. Or you will have to download ERA5 yourself, which I don't think we will do. And import ERA5 variables. Few variables I'll download and compute. Oh, okay, so probably I should have mentioned this before mentioning the outline, that what we are going to do is we're just going to look at the stability, specifically Brun-Weisela frequency. So, I mean, if you remember from morning's, I mean, the talk before lunch, Adrian presented a Richardson number where the numerator was Brun-Weisela frequency, I guess. So I'll be plotting a Brun-Weisela frequency. It's just, it's an indicator of the stability of the atmosphere. And so if you have a negative value of Brun-Weisela frequency, then our atmospheric column is unstable. If we have positive value, then it's stable, but lesser the value, less the stability. And yeah, that's what we are going to do. And for Brun-Weisela frequency, we will need few variables. We'll have those variables, and then yeah, with those variables, we'll essentially compute potential temperature, virtual potential temperature. So our Brun-Weisel frequency is G by theta and d theta by dz. So for that, we will need all those variables. So now a logistic question: how do we do this? I can either right click on it and create a QR code that you all scan and get it in your computers, or you code it yourself. So those who like to code, don't scan. Those who like to take my notebook, you can scan. And I have loaded the data in a way that you can access my Google Drive. So you don't need to download it or save it in your own drive. So that should be, and yeah, what I would suggest is, because I already have the notebook ready, sort of. So you can, after we go through our my notebook, we can discuss what additional things you would like to do. Or maybe you can utilize the variables yourself, whatever I already have, and use that to cook up something yourself, and you can discuss the results if you find anything. It's just same time series plotting, same variable. I do not have many variables anyways, so that's what we're going to do. So please let me know when you are done scanning, so that, and also let me know after you can actually access my code or not. Oh, yeah. Can you chat? Okay, sorry, not can you chat. Can you paste this thing in the chat? Yes. Then online people can. But if I'm sharing my screen, they can actually scan from their screen. Yes. I think some of the new laptops are very intelligent. If you take a screenshot, then it thinks as scanning, and they take it from there. So we all have access to the notebook. So I'm going to start. Just stop me if anybody is still working on or struggling to access the code. Yeah, I'm going to just unfold block by block, and then so I think I already just briefly mentioned that this is what we'll be doing. We'll compute n squared. N is the letter used to indicate Brun-Weisel frequency. And we'll compute n squared. And it's G by theta v, d theta v by dz. And for theta, we'll need temperature. For theta v, we'll have to include specific humidity. And of course, for z, we'll need the height geopotential. And then time, of course, will come with it. And of course, pressure level as well. So, oh, by the way, I just bypassed downloading ERA 5 because logistically it's not possible for us to download ERA 5 at this point of, right now, and then use it. Those who are working with ERA 5 already know how to download it. Any of you who do not know how to download ERA 5, there is an excellent video by Adrian Tompkins. I think Adrian Tompkins maintains a YouTube channel. I forgot the name of the channel, but just, I mean, I guess you are smart enough to find the YouTube channel hosted by Adrian Tompkins. And he has a very detailed, except sharing his password, he has told everything. So load the pre-downloaded data that, so you can see that this part I have commented because this is what I was doing when I had the data in my Google Drive. But what you will be doing is, but one thing I'm not sure, when you access this, you are just seeing my code, or you could copy it to your, you made a copy, right? Because I have given all of you, I wasn't sure, so I have given all of you like edit permission. So if you edit it, then I won't be able to process with it. I mean, proceed with it. So you can copy. I'm assuming that all of you know how to use Google Colab. If you don't know, then probably just when we are using this code, you will learn it because it's just doing Facebook. So this is the part that I did additional just so that all of us can could access the data that I have in my Google Drive. So I learned from ChatGPT that if you click on a shared file, link to share the file, in that link, there is this thing which is called ID, which is a field between d/ and view. And if I did it right, I thought I will just ask you for fun to write this, but I think it will be too much. So if you have copied and if you run it, can you access the data? That's the question. You could? Okay, you can speak as well. Okay. So you can access or access the data. I need 2 more volunteers to speak up so that I know. Yes? You had less food during lunch? Or is it my ear? So you did? Okay, great. So just not to spoil the fun, don't please open the blocks under each headline. Otherwise, there will be no point me speaking and going through this. So this is probably what, oh, okay. I think something happened, or did I not? Yeah, I'm just, so are you getting the same error as, are you getting the same error? Okay, I think I read it like this. No, actually, I was doing with this. Uh, Did I? This is not needed. Okay, thanks. So, yeah, because if it hadn't worked, then there was no point sharing the QR code because then we would have all be looking at my notebook. So this is the data that I have downloaded. And we have time steps. And it was important for us to look at this because I don't know why I think what I did during downloading, or maybe the data had these names, like instead of time, it had valid time. For pressure, it has pressure level. So that's the reason why I thought I will just show the data so that you can do it. So next, what I will do is I will compute area means for that region that I had mentioned before. I'll just do an area mean to, I'm just not caring for any spatial variability within that box. I'm just, so like, yeah, I'm just considering the whole box as one and doing area average for all the variables over that grid box. So I'm just going slow because you already have the code. You can do it, see it and just run it. But just in case, if you're finding any issues, just share with us so that if anybody else is also facing this same issue, we can share. And next part would be to compute height from geopotential data that I have downloaded. This probably I wouldn't need immediately, but I have just calculated it because later, maybe I might have calculated later as well. We're doing good.
So how did you sort out the DS underscore temperature issue?
So, oh, hi. Oh, I had to copy this part, this block below.
Okay.
After this one.
Okay.
Actually, I was using this part before, and this is the path to my Google Drive.
Okay.
And later when I commented everything, when yesterday I tried, it worked because already the variable was already in memory, so it accepted this block. But anyways, so this is, short answer is you need to copy this block. Anybody else is having the DS temperature issue? No, right? Because this is the only editing we have done. So we loaded the data. We have done area mean. And the last thing, latest, what we did was computed height from geopotential. So this is just geopotential by G. And then we'll compute potential temperature. I think most of us are already doing some coding, simulations and everything. Can we have some comment on potential temperature? What is it? I'm not going to give the definition today. I'll just show the formula if you want. So this is what potential temperature formula would look like. This theta, which is the usual notation for potential temperature, equal to, where is it? Yeah, equal to 1000 by P raised to the power 0.286. So just tell me what 1000 stands for. Okay, great. And now the more difficult question. What is 0.286? Okay, then why didn't you tell anything when I asked about potential temperature? So now I think it is pretty straightforward for us because we know Python, we know what this code is doing. And potential temperature, theta equal to T multiplied by 1000 divided by P raised to the power R over Cp. That's what we did. And then we plotted this theta. So this is our potential temperature profile. And now what would be our next step according to the outline I shared? We'll compute what? Virtual potential temperature. So did we take a photo of this? Okay, good. So my temperature is increasing and height is increasing. And this is my, I think my theta looks something like this. Okay, now I will, with this red chalk, I'll draw theta V. Can anybody tell me how would I draw it? Okay, so my theta V, so this is A1, this is A2. What would be my starting point for theta V, A1 or A2? Raise your hand for A1. A1? Oh, you are too far. So this side is A1, this side is A2. Where will I start? A1? Okay. So theta V, so others were for A2. Okay, so you were the only one who did it wrong. Don't worry. So, so when I will include the effect of moisture, then my temperature will have a higher value. The theta V will have a higher value. So I will start from A1. Oh, sorry, A2. Thanks. I'll start with A2. And so again, this is middle point is B2 and B1 and C2 and C1. So next point will be which one for theta V? B2 or B1? So I started from A2, sorry, I think it's definitely not clean. I'm wiping off the, okay, anyways, B1 and B2, I think it should be clean. Sorry? B2, we have, so I have one voter for B2. Anybody else wants to shout for B2? Okay, I see 3, 4, 5 people for B2. Anybody for B1? Okay, good. We have no person who did it wrong. So we agree that it should be B1. And now tell me whether it will be C1 or C2. That's the trick question. Okay, I failed and you passed. So you could crack the trick question. Can anyone explain based on what we did specifically in my slides? So what I showed was, if this is equator, my moisture plot was something like this. And then beyond this point, moisture was almost practically zero. So all the effect of moisture that I'm going to incorporate in theta to make theta theta V, that effect will be seen only at the lower levels. At higher levels, there won't be any effect. So this is what we're going to see. This code is practically, this block is practically done. So theta equal to 1 plus 0.61 Q. So this will, now I have computed theta V from theta. And when I plot theta V and theta, this is exactly, so we started from A1, we went up to, A2, we went up to B2, and then beyond that, theta V and theta, they are almost same. So in your copied Colab notebook, you could plot it. It runs. Anybody who didn't use Colab before? Oh, okay. But you are doing good, right? Yes. So, and now we will plot or compute Brand-Weiser frequency. So it's the, I think I should have and could have made the fonts bigger. I think you can still see my n square, g by theta v, d theta v by dz. Should I make please tell me if I need to make the fonts bigger. So yeah, my code just does what the formula shows, and it should be pretty easy. And so here, just for the sake of plotting it in a nicer way, I just installed MatPy, which gives us nice units and everything for meteorological variables. And okay, I need to keep running. Even if I don't run, I think it's fine as long as you were running. So from MatPy, I just imported units. And this part is just to show you that if I check the units, then n squared gives me dimensionless units. And I learned that this is because of stripping of units by differentiation. So this part is just to decorate the ornaments of n square. I have just given it name n square and yeah, given a nicer name, and 1 by second square. And I probably should have plotted my n square as a whole, or the whole height and time cross section of n square before coding or before showing the boundary layer. But I think I can show it now. Yeah, I just wanted to plot my boundary layer Brun-Weisel frequency. So I took n square and just computed its average below 2,000 meters. So that's. So now I'm visualizing my Brun-Weisel frequency with pressure and time. And oh, I do not have my boundary layer yet, which is good. I thought I already had overlaid my boundary layer here. So now we have our event on 19th May. And so somewhere here. And it starts from 10th May. And then we have, oh, my Siri got activated somehow. But anyways, so we have this vertical levels, and then the time. And then what do we see basically? Can anybody look, like, I mean, you didn't have to code, so we can discuss a little bit. What do we see in this plot? I think we need to pass the mic. It's otherwise this room is a little too big and it would be unfair.
Yeah, I think you can also ask people to speak up.
Pinpointing.
Just the speaking, I think, is good.
Okay, then we can start with your policy from IITB people. Okay, don't worry. I'm not asking you to tell me any physics or meteorology of it. I just want you to tell me where do you see white and where do you see red.
So we
Yes.
see increase and decrease in Brun-Weisel frequency
Yes.
between 900 and 800 hectopascals.
Yes.
And it's very almost constant below 900 hectopascals.
Yes, that's very nice. And increasing and decreasing, increasing and decreasing. And then there is, I do see a slight darker shades at the middle layer. I mean, I'm not, like, I haven't done any case studies like this, so don't expect me to explain everything. I'm just telling what I wanted you to tell, that I see slightly darker shades and lighter shades. And I see repeated, what already you said, repeated strengthening and weakening, or white and red patches of Brun-Weisel frequency. So when I see such a clean or such a strong signal of very nice repetitions, then what I decided is to plot that and to have more like a better understanding of how this matches with my precipitation time series. In your code earlier, you might have already seen that I had downloaded precipitation data as well. Somebody who commented that precipitation from ERA data is not that good. Somebody yesterday commented, but I was just lazy. I downloaded rainfall from ERA 5 just for this exercise. So next, what I will do is, I have written here plot with precipitation. I just I already had loaded the rainfall data. I just converted it to millimeter per hour. And yeah, I think I had computed, and I defined some plotting limits. And because my n square had some excess height and time, I just did a transpose. You can always go through this code. I don't want to, I think we all know Python. So yeah, this is the plot that I wanted to show. I thought, so this repeated oscillations of boundary layer Brunt-Weisler frequency, that is plotted in the blue line, and the rainfall time series is plotted in black, and then we all have the shading as before. So yeah, now probably we can have some comments on this. So Courtney, I think very briefly she mentioned towards the end of her talk something about, very briefly, about diurnal cycle. I think we haven't had any discussions on, like, longer discussions on diurnal cycle maybe. Oh yes. Oh yes, we have got a targeted we have got a target.
Yes.
So don't worry. I mean, whatever you say, it will have to be correct. So now,
No, I might be wrong. So what you are asking, right?
I mean, just anything that you can see. We have two time series showing repeated kind of fluctuations. And do you see any, if you see any correlation between blue and black? Yeah. So we just, so these oscillations in I probably could have plotted one more thing. Maybe you can just tell me, if I have to explain this Brunt-Weisler frequency oscillating, like, or increasing and decreasing repeatedly.
I think they are sinking almost from 13 to 21. Like
13
there is
to-
a peaks, they are almost in a sync.
Yes, yes, the peaks are almost, not exactly.
Not exactly, almost.
Almost in sync. So the precipitation sort of, precipitation peak, if you notice, this gives these, probably I should have plotted the blue line slightly below, then it would have been easier. But nonetheless, these peaks actually help us to see that the precipitation peak appears after the dip in the Brunt. Yes.
You off?
No, that's fine. It's better if you speak than I.
No. I mean, should I speak or?
Yes, of course.
So one thing I observe is that even near the surface, like around that 800 to 900 HPA, which is like denoted by 1 to 2 kilometer. So the white patches. So those are practically the region where Brunt-Weisler frequency is 0 or around 0. And one thing I have to ask is that the purple lines, are they the averaged Brunt-Weisler frequency from 0 to 2 kilometer?
No, actually, I think it is just 2 or averaged.
Is it averaged or is it at 2 kilo?
What does the code say? Can anybody tell us? What did we?
The legend says averaged 0 to 2 kilometer.
Yeah, it's 0 to 2. So I'm assuming that it's average.
Yes.
So both are actually in sync with each other. So wherever there are white patches, around the same area, the Brunt-Weisel frequency from 0 to 2 kilometers also taking a dip.
Yeah, so
So, and exactly, not exactly, but very much around those regions, the rainfall spikes. So that tells us, so when Brunt-Weisel frequency is positive, it's greater than 0, so there is oscillation in the atmosphere of the air parcels. When it is near about 0, so the air parcels are, I won't say stationary, but there isn't an instability as such. So, and the day of the extreme rainfall on 19th, we see that the Brunt-Weisel frequency, the range of the dipping is quite greater compared to the period after 19th May, where the dip, the range, it decreases. So maybe something was building. There was oscillations actively.
could be, maybe. I mean, there was rainfall eventually, so something must have happened. I mean, as I said, this notebook is not to explain everything that happened before or after. What you said is absolutely like a nice detail observation, that what you noticed, that the dip was deeper, or maybe this was slightly higher, or I don't know. I mean, we are free to interpret it, but eventually yeah, I think there.
If it is unstable parcel, if it is unstable, it should go on rise. The oscillation should be very less. But let's assume that the parcel is warm and is going up, and once it becomes cold and denser, it comes down. So again, if it, based on the environmental lapse rate, if it is about the mean, if it is oscillating, the oscillation should be very clear about the mean. So when the oscillations are very well prominently seen, that means it is, the parcel is not going unstable. I mean, it's not unstable yet. So when the peak, if you see the peak rainfall or 19th or 18th, that oscillation when the rainfall is peaking up, you can see the oscillations are reducing. That's what he was mentioning also. So it's go on increasing. The oscillations, the stability, the frequency of the oscillation should reduce theoretically, as far as the n square is concerned.
Nice. So yeah, I think what I saw the first, that the rainfall peaks just followed the Brunt-Weisel frequency dips, and honestly, I was expecting. I don't know, really expecting is the word, but still, based on what we learned, I was thinking I would get some blue patches somewhere, but it's all positive. Nonetheless, there are increasing, I mean, larger and smaller value, which says that just before precipitation, there was a dip in the Brunt-Weisel frequency at the boundary layer. So there was less cap for like less force prohibiting precipitation or convection rather. So with that,
Bidyut, I wanted to add one more point in this. So our notion that Brunt-Weisel frequency being stable versus unstable, and convection and stable, I mean just oscillations being orthogonal to each other. This is probably true for dry convection, right? All our theories,
yes,
especially about this, is dry.
yes, yes.
But when moisture is there and when precipitation processes are active, the convection and they would get coupled. So, I mean, as we are seeing here, I guess that we are finding it hard to really separate out the sign of n squared and corresponding rainfall. Yes, rainfall.
Yeah, Dr. Mohan had something.
Can I add? I mean, like, yeah, this is dry convection, the oscillation is good, but that's why we are using theta V, virtual potential temperature, where it is conserved quantity in both dry and moist. Maybe that could be,
No, I think atmosphere is conditionally unstable, right? Then, so just theta V wouldn't answer the. I mean, that's my thought, that theta V probably wouldn't answer fully why there should be a sync. But that's why this plot is very interesting.
Yes.
Probably that's the motivation. Yeah.
So you're, I mean, I learned more than probably, I don't know how much you find meaning in this plot or how much you're going to use this code. But for me, when I was plotting this, I felt like, okay, like from just reading n square values to plotting it was a nice learning experience. So just feel free to keep commenting because, I mean, that's what makes a lab different from a talk.
So may I?
Please.
Yeah, so I wonder what will happen if instead of virtual potential temperature, we use equivalent potential temperature.
Just
Whether
code it. Just you have the code.
I don't remember the formula for that. I have to look it up.
Okay.
If we use that, maybe because that is also a conserved property for moist air parcels.
So the best way to get your equivalent potential temperature would be use the MetPy package. It should have it. So
So this, there is a very nice derivation in David Randall's book on this. I think the title of the chapter is Up Moist, Down Dry. That's the title of this chapter in the book on general circulation of atmosphere. And I think the argument that is made is that you cannot simply translate what you did for theta V to theta E in the moist case. That is a nice, this I think these notes are freely available on his website. You could check it out.
okay, thanks. I think
So
that's.
I have a doubt. Is the time delay between the blue and the black curve, like the peak of the blue and the black curve, does it has any physical significance? Because rainfall comes first, and then the peak in the rainfall, and the blue curve has a peak towards left of it, right?
Yeah, towards left.
The peak, the highest point in the blue
This one.
curve, the leftmost, like 2-3 oscillation.
This
Yeah,
one.
over there.
So this
Peak and the
means
peak in the
high
rainfall.
value of Brunt-Weishaler frequency. So higher value would mean that you have a higher prohibiting, like higher, what do you say, cap on convection. So that's why your precipitation peaks only after there is a dip in stability or decrease in stability.
We can plot it in nocturnal rainfall pattern, like evening and morning. Then that curve maybe will be okay.
Okay, you spoiled my game because I wanted to ask what are you going to do next. So, anyways, thank you.
Excuse me, I have a question.
Oh yes.
I don't know why the near the surface is positive and it doesn't show the diurnal variation. So we can see the diurnal variation near the height level between 1 kilometer to 3 kilometer, but below that,
Oh,
near the surface, it's
near the surface.
Yeah, it is.
Yeah, can I comment?
Oh.
Yeah, that is probably because it's here.
Oh, okay.
This is Bangalore, right? So we have a topography that's around 1 kilometer. So in ERA 5, it should be extrapolated below the surface.
Okay.
So probably that is the reason the values are same and that's.
Okay, so if we limit the analysis to the ocean or something,
I think it should be fake or undefined or something.
Oh, okay.
I mean, that's a good point. I couldn't have answered that.
Yeah, thank you.
Thank you. So next already what Pradhanji said that, okay, yeah, we would just do, because we see, what I'm going to do is I'm just going to do like a climatology of all these days. So I'll just do a diurnal climatology for the 10 days. And so I'm just skipping the coding part. So now probably what we were trying to conclude from visual inspection, like where the dip is, where the peak is, I mean dip of run-Weisler frequency or dip of stability and peak of rainfall, I think this make more sense now to us that there is, so this is, okay, I did something in addition, not in addition, but I just converted the time to IST because that's something, that's a key point. Even though it's a small calculation, you just add 5.5 hours to UTC. But if you do not do that, because we are talking or we are trying to see the diurnal cycle, we need to have the local time. That's, I find it, personally, I find it the difficult part of my calculation that if I want to see a diurnal cycle, as long as it is over 1 point, it is fine because it is in a one time zone. But if I have to plot something, a diurnal cycle in the whole globe, then we need to ensure that at every point, what we are showing is relevant to the local time. So dealing with local time zone, I think with now with this Python packages, it has become much easier, I think. So, but just to make the point, we should always keep in mind the local time when we plot the diurnal cycle. So now I think it's almost pretty obvious that we have this increase in or decrease in stability because we have a lot of sunshine or heating of the surface at the post like afternoon hours. So this is 3 p.m. And then when we have the lowest of stability, precipitation has the, or convection has maximum chance to grow. And that's what we see here. So now from a reasoning point of view, this is the climatology of 10 days. And this is, we have plotted, or we also had seen in the shaded plot. This has been happening for almost, this was happening for almost the whole week or whole like 5-6 days before 19th of May 2025. Then what would you like to do next to see what probably have triggered or why? Yeah, I think somebody might have already guessed my question. So what made it trigger on 19th and not before? So how would you investigate or how would you like to investigate it? Yes, please.
Maybe we'll have to look at the intra-seasonal aspects.
Yeah, so I think addressing event-wise case studies for like something like this, there are two aspects of looking at it. One is large-scale drivers, and what was the synoptic scale status, and then the other one is just the thermodynamics at that location. So when I asked what you are going to do next, actually I was thinking in terms of thermodynamics, but you answered it in terms of large scale or synoptic scale dynamics. So you were not wrong, although that is not what I actually had asked. So if I have to specify what dynamics or what thermodynamics you would like to investigate, because this was happening. So if we have to take one guess that, okay, this might have happened only on 19th or at least 18th or 19th, then what would we guess or suspect? Sorry? Moistening, or I think we can keep one mic there. Oh, okay. I heard it, but I think the people behind
Just
it.
that, like, if thinking on that time scale, it could be that the column will have to be unstable for the strong updraft and the convection to happen. So you need moisturing or like warming from the surface level. Oh, because it's May, I think it's warming probably. I don't know. Just guessing.
Okay.
And
So-
moisture should be there, obviously.
And what should be? Moisture should be there. Yeah, so I think I actually looked just one step. Yeah, by the way, thanks. What you said is, so this is something I checked, and because I thought this was like, this is what yeah. So now you can see that there was this oscillation of stability and instability, or maybe repeatedly the air was becoming unstable. But then when I plotted mid-level moisture, so in Adrian's talk, he mentioned that convection refers if the mid-level is moist or if there is a cold anomaly in the mid-level, then that can cause precipitation. Courtney also mentioned I think in different instances, not very specifically. Tomorrow morning, Bolum is going to talk about his SMCM, and then also he will talk about this mid-tropospheric dryness as a key variable in his SMCM. I hope he will talk about that. Otherwise, discuss with me. I will have to talk. So yeah, so you can see there was this moisture building until 19th of May. And the same amount of instability was enough on this particular day because the mid-troposphere was much more favorable for promoting or for having a convection. And then all the moisture that was accumulating was realized on that particular day or those couple of days. So, yep.
Do we see a lead lag between moistening and rainfall here? Because it could also very well be re-evaporation of falling precipitation that's moistening mid-troposphere.
Maybe. I think I was too linear here. But yeah, maybe. This is, I mean, I thought I will ask you to do this as a task, like what you would like to see. And then because I thought, I felt curious and I just thought it's just one line and I can see it. And then I plotted. And then during lunchtime, I thought I will delete this part and ask you to do it. But then Adrian took a little more time. And then I thought, okay, let it be. So you can see this thing. And now we really do not have anything more that I have already done. So this is the end of what I have done. And next is, I think we have used up the time we were allotted. So I'm not expecting or I'm not asking you to do anything at this point, but you can always tell or share your thoughts, what you would like to check further, because we are talking about a convection, I mean, heavy rainfall event. And there will be some thermodynamic, dynamic variables that probably you can plan to check. And also like Gokul, right? Gokul mentioned that large scale meso phase, you said? Yeah, so monsoon ISO phase. So, and yeah, you can check anything. I mean, feel free to check anything, any variable if you like, you can download and check the time series, or maybe you can plot any large scale fields that you would like. But yeah, share your thoughts if you are already thinking about anything. Yes, do you have the microphone? I think we need the microphone there.
You have mics, right? Yeah, please, yes.
Yeah, I think this is what I mean, like, We're working on similar kind of a thing. It's again, it is reaffirming that the boundary layer moisture, whatever we see in the extreme events, it is only to trigger the convection, but it is the free tropospheric moisture that is what the enhancement of the growth of the convection is mostly happens. So it is also the Chris Brotherton and Holloway and Nealon's 2009 paper. They are also saying that the free tropospheric moisture, the bulge in the sensitivity of the free tropospheric moisture to the extreme events or the rainfall. I think it's pointing to the same thing. See, the free tropospheric moisture, specific humidity, the importance of free tropospheric moisture in the extreme event analysis, rather than the boundary layer moisture or the large scale convergence. Maybe it's a trigger, but enhancement would be because of this moisture. It's just to add a point.
Yeah. Great, thank you. So yeah, I mean, my notebook ends here, and from my side, I have explained whatever I did. So now it's time for any discussion that you might like to have.
Bill's advocate, actually, just for the discussion's sake. My proposition is there's nothing special that happened on that day. This happens usually on on most of the days where gradually convection builds up. There's nothing special that happened on this day that we have seen that may have led to extreme rainfall. And this question is not to Bidyut. This question is to you, and you have to prove me wrong and show that this day was different than many other days. For example, Mohan has given one thread already saying that you probably would not see as much moistening at mid troposphere if this was a standard rainfall event, but especially during extreme events, such a mid tropospheric moistening is seen. And the second thing would be to show that this moistening happened first and then rain episode happened. So I think there are already two sets of analysis you could do on top. I think one is contrast this against climatology, diurnal climatology for that day.
I think
across
Eric,
many years.
I see Eric wanted to comment on anything, and then Gokul also have raised his hand.
Yeah, I agree with that too. I mean, the other thing I'm curious about is CAPE and convective inhibition, because I know that it looks like the Vaislav frequency right above the boundary layer increased. And so I'm wondering if SYN convective inhibition went up, that caused there to be a spike in CAPE during those extreme events. And it'd be really interesting to look at that. I'm not coding it up myself, but very interesting for somebody else to look at.
Yeah, so actually yesterday when we were floating our projects, I thought I will show this and ask some people to plot CAPE and SYN, things like that. But I think people have already picked their projects. So yeah, anyways, yeah, Gokul, you wanted to?
Actually, there are students who will work on extreme rainfall event, right?
Yes.
I think, I mean, if some of them want to volunteer and prove us wrong, prove Eric wrong that SYN didn't play much role, prove me wrong that this is indeed special and it's not just the ordinary day in Bangalore.
Yeah, I have a proof, like it's a kind of some intra-seasonal wave that propagated over the southern parts of peninsular India. So maybe if I can come and show it over the screen.
Oh yes, I mean,
yeah, we have online like
websites.
Yeah. We have analysis available for the past, so we can check.
Yeah, fantastic.
So yeah, you can use this browser to open this. But I have just kept the links of IMD. They have this video where you can see there is this large depression over whole southern India part. So it was just, I think, part of the whole big synoptic scale system. So yeah, I didn't show it because then people would find yes.
So yeah, I think it's visible, right? So here is this climate monitoring system from the JMA website. So we can go for the Asian region. And so this event occurred in 2025. So we have a 5-day mean here, and the date closest to the event is so I'll take an average of 19 to 23. And I'll show you the vertically integrated moisture flux convergence anomaly here. So you have a circulation here. And also let me plot the theta E anomaly as well. So you see there's this kind of a positive anomaly that is to the northwest of the rainfall anomaly.
Can you do control plus so that the...
Yeah, let me. Command plus, right?
Yeah.
Yes.
But
in back command.
okay, I think plus is missing here because it's a German keyword.
Yeah, so I think, let me just,
No, have it, but the layout is English one for me. So I just remember it.
so we can see that I'm just animating a 7-day anomaly. So we see this kind of equatorial anomalous westerlies in the Eastern Indian Ocean. And then as I move further, you can see a kind of cyclonic circulation that will move northwest, and that's moving, crossing the southern peninsular India, and sort of it move towards Arabian Sea. So this was declared as the monsoon onset phase back then, a year ago. So I think this intra-seasonal wave that was propagating is probably associated with that continuous extreme rainfall or some anomalous event that took place over Bangalore. So after that, it just...
Yeah, I think onset phase sounds.
Yeah, it was onset
because
phase.
that's when the onset happened.
Yes, yes.
I think part of my skepticism is answered here. I think that I know that in Bangalore, 19th May to 23rd May, climatology is definitely not this. So this is anomaly.
Yeah, it's
so large scale conditions probably were favorable is your argument.
Yes, yes.
Sure.
Okay, so I mean, those of who wants to just for fun look at this event. Oh, okay. There is a. I think there is a mic already there. Or is it?
Sir, I want to tell that extreme rainfall event always associated with deep convection. So when there is a extreme rainfall event is happened at 19th, so you can see that the Barnweisler frequency at the upper troposphere is continuously getting toward a lower values, means low stability in the upper troposphere. And it is not prominent in other cases. In the other peak of the rainfall, you can see there is a increase and decrease of the Barnweisler frequency from the lower to the upper troposphere. But in case of at the 19, you can see that there is a continuous decrease of the Barnweisler frequency from the low to upper troposphere. So I can say there is a high instability at that moment throughout the altitude. So it can causing this deep convection and
Yeah, I mean, this can. Okay, I should have put the plot. This can, but I mean, the whole idea of this notebook was not to explain that event in its entirety. Neither the aim of any analysis is to fit the results that we get to what we have observed. There might still be some unknowns. We might still not be able to explain it, but we just do an organized, robust analysis of it. And we just need to have the framework to analyze it. So if you see that there is a decrease of Barnweisler frequency or a decrease of stability at the upper levels, then yeah, you can just further investigate it. How much is it reliable or what does it actually mean? But because it's a lab, I thought I'll just show how to start addressing a problem. And when you don't find something, then we just start thinking what might have happened. And like Vishal mentioned, what was the climatology, and maybe you just take, instead of a climatology, you just take a typical Bangalore day or a lighter rainfall Bangalore day and do the same analysis. And then probably you would exactly find what Vishal is saying, that this is anomaly, or maybe you will find something similar happening. And maybe there was something else who was driving it. Like Gokul said, there was some a large scale was the driver. So yeah, that's the whole. I think we succeeded in generating some turbulence in the room, and yeah.
I'm just floating an idea. Is there any way we could have predicted this?
We could have, means we didn't, which I think is not true, because IMD forecasted and with like their weather forecast. I think IMD did forecast. If you look at the Facebook page of IMD and look at maybe 1 week before, the bulletin from 1 week before, then probably you would see it, right? Or
wave was predicted well,
yeah.
but the localized extremes, that's still
not. Okay.
not.
Okay, then maybe, yeah, but I do not know if I did a good job of answering properly your question, but
No, fantastic job of triggering several set of thoughts, I think. Actually, this question, I think there are several extreme events that the model captures. The problem rather is that there are too many. Many a times there is false alarm ratio is quite high in model.
I think somebody was telling during yesterday's introduction that we get so many events. It's not that true ones are not captured. The problem is we get too many false alarms.
So many a times problem
region
wise is that there are too many events predicted, and the moment you give, I think, warnings and event does not happen, you know what all we do. We used to do, right? That we say, nothing happened. We are preparing just for nothing. Yes. I guess similarly, there was, I just wanted, just for the discussion, there was a crazy rainfall event in Germany, and all the disaster authority was informed about this, but they also kind of didn't pay attention, and the event was realized. So I don't know what are the numbers for false alarm ratio there, but looks like also quite high in Germany. Yeah.
Yeah, I think, yeah, probably Divya can comment. But I can tell for Exeter, there's they rarely miss, at least for weather. Oh, yes, sorry. The blue, so you were referring to the shaded plot?
Yeah, so I expected there would be blue patches because of like negative Brunt-Weisser frequency showing instability, but there's none.
Yeah, I think you and me, we thought our thoughts resonated, but Vishal explained that our thoughts were dictated by what we read about dry air. When there is moisture, then
Right, like anyways, and we are using theta v.
Theta v, yes. Mohan added that, but still moisture. Yeah, I don't know how to explain, but
we should rather say that even if you have discounted,
non-negative.
Yes, discounted the fact that moist convection is conditional instability, we could still explain so much. I think that's the way to look at it, because once it's conditional, it's a nonlinear problem, right? So even with linearity, we could do so much. I think is
conditional doesn't prohibit entirely. You can still, if you fulfill the condition, you can still avail the precipitation. Okay, I think we are wrapping up the session.
Yes.
Then next, what's in agenda?
Yes, so thanks. Let's thank Bidyut for a very nice session.
Thank you.
Somebody wants to make a comment?
I would ask rather.
Yes.
Can
you keep it short so that
yes, definitely.
Yeah.
I would rather ask, I think Brunt-Weisler frequency is not defined in the negative. So it is 0 for neutral. It is positive when the atmosphere is stable. When it is unstable, it is not defined.
Yes,
So
because your solutions become imaginary.
yes. So we
Yes.
will not see blue patches just like this by plotting.
Yeah.
They have not.
No, this is squared.
Yeah, then we won't. How will we see negative?
And squared negative is the, again, for a dry convection.
Yeah. Okay.
Okay, let this be up there and we can.
That was a nice session. I think we could break for coffee.
Yes.
And come back at 4 o'clock. I think the sole goal we would have for the 1.5 hours is you all to have committed to a project you would want to do in these couple of weeks, whatever is remaining. Sorry.
Then
there is one correction
one talk
in
at
what I
5,
said.
right? Oh, sorry.
There is a talk at 5 o'clock by
Alison Wing.
Professor Alison Wing at 5 o'clock. So we'll stop a little bit early, something like 4:50ish. So we will have around 4 o'clock to 4:50. So we'll have around 50 minutes to finalize this. But we will all want you to have committed to a project, and you could say what project you would want to do in that document that we shared yesterday. So say the title of your project, your potential mentor, and your name. That would be nice. Sure, we could do that. I think ICTS is right now making a group of all of you, and they're going to have a group ID so that we all could then.
Yeah, just be back before 5. Okay, we don't want our online speakers to wait because they will be logged in time, and they will be speaking at a very different hour.